to begin it with an insightful quote by Professor Kip Thorne, who was a 2017 Nobel laureate of physics. He said that the most enjoyable part of science is actually doing it. So today I shall walk you through the work that I have done under the exceptional guidance of Professor Sagar Mitra. My dissertation covers basically the development of lead oxide cathode materials for next generation sodium-ion batteries, and the title Mechanistic Insights of Heteroatom Doped Lead Oxide Cathode Material for Next Generation Sodium-Ion Battery is the main essence of this investigation. So in today's presentation, I shall start with a brief introduction of the working principle of sodium-ion battery, followed by the lead oxide cathodes, their classifications, the major challenges faced by them, and then we shall delve into the 4 working chapters of mine. And finally, we will have a comparative study of whatever the work that we have done. So starting with the working principle of a transition metal oxide: moisture stability, environmentally benign property, and cobalt-free composition. In spite of having these advantages, this particular cathode material is still far from commercialization because of the certain hurdles. The major one being phase transition at higher voltage. So if we visualize the first particular layer of oxygen and ion in this particular manner, and then position the next one exactly above the other, the voids that forms are prismatic voids. And the front view would look like this, in which we have inserted the sodium ions. Thus, a prismatic void is formed out of 6 anions, which looks like a trigonal prism. So during charging, when we are extracting the sodium ions from the cathode material at a higher voltage, when the amount of sodium ion reduces from 0.67 to 0.33 to 0, because of the weakening of the electrostatic cohesive forces, the slabs of the transition metal glides and forms octahedral voids instead of prismatic voids, and making it the reinsertion of the cathode materials difficult. So another problem is that the partial irreversibility of anionic redox reaction. Although anionic redox reaction has been a boon for the sodium-ion cathode material, which can make it complementary to that of the lithium-ion battery cathode materials, however, it comes with its own sacrifices. The first and foremost being the irreversible capacity loss because of the loss of the oxygen from the lattice and leading to structural distortions. Another problem when we try to activate the manganese in the cathode material is transition metal dissolution. These leads to consequences such as structural degradation, volume change, gas evolution, and poor electrochemical performance. Keeping these challenges and consequences in mind, we designed our thesis in such a way that we will start by identifying the major challenge of the P2 type sodium nickel manganese oxide, then recognize the driving force behind it, and finally we adopted the strategy of doping and dimension reduction in order to deal with this challenge. Then further, in the next working chapter, we actually unleash the effect of heteroatom doping in order to elevate the cycle life of sodium-ion batteries and have an in-depth study of that mechanism. In the third working chapter, we dealt with the challenge of irreversible oxygen redox reaction by adopting the strategy of doping a high-valent heteroatom and thereby probing the mechanism of anionic redox activity. And finally, we bracketed out the best performing cathode material and then further improved the performance over a wider potential window by embracing the strategy of coating. So in the first chapter, we dealt with the problem of diffusion-induced stress. We have seen that in the consequences that exfoliation is the major problem which comes out of the irreversible P2O2 phase transition, leading to rapid capacity decay, large volume change, and mechanical degradation. It is to be understood that the major root cause of this particular degradation is the diffusion-induced stress, which is introduced when the alkali ions diffuses during the extraction and insertion, and then the energy is then released in the form of cracking, crumbling, or exfoliation. Hence, we understood that particle size and C rate has a crucial role to play in order to make mechanically robust cathode materials. So we adopted the strategy of doping. In this case, we doped titanium and followed the strategy of dimension reduction. So we have abbreviated this particular cathode material as NMTNO, and the nano has been derived as NMTNO nano, and the micron as NMTNO micron. So we start by synthesizing the cathode material through the microwave-assisted solid-state technique, and through the XRD refinement, we confirm the phase, and then we try to hypothesize the advantage that the NMTNO nano would give us. So we hypothesized that the NMTNO nano would actually make secondary particles which would be quite porous in nature, leading to excellent electrolyte percolation and enhancing the sodium ion transport pathway. However, the secondary particle formed out of the micron-sized NMTNO, the electrolyte percolation would be limited only to the surface of the secondary particle. Thus, we validated it through an experiment of contact angle measurement, and through this optical image, we can see that for the same amount of time, both the NMTNO nano and micro electrodes, when we drop the same amount of electrolyte, the nano absorbed the electrolyte easily, whereas that of the NMTNO micro still contains the bubble. We further confirmed the position of titanium doping through DFT analysis with the help of Dr. Gayatri Barik, and we saw that the titanium is doped at the manganese site, and through the PTOS calculation we observed that doping titanium has also enhanced the electrical conductivity. And finally, we also validated the air moisture stability through the XRD refinement. We had taken the asynthesized powder and exposed it in air and immersed in water, and finally acquired the X-ray diffraction, which shows that the majority of the bulk structure remains constant. Further, we analyzed the morphology through scanning electron microscopy, and through the SEM micrographs, we can see that the primary crystals are almost hexagonal like plate-like structures with clear facets and uniform geometry. As we had hypothesized, the secondary particle formed out of is quite porous in nature, in contrast to which the NMTNO micro gave us a bigger, which was around 5 times bigger than that of the nano, and also quite non-porous in nature. We also observed the electrode through the cross-sectional SEM and observed that the distribution of the secondary particle was quite uniform, and through the elemental analysis we saw that all the elements were uniformly distributed throughout the electrode. Through the transmission electron microscopy, we actually saw the primary crystals in a better way. So we saw that the primary crystals have hexagonal plate-like morphology as seen in the SEM as well, and it was seen to be quite well interweaved with each other, which suggests that it has a better structural stability and a regular geometry. Through the high resolution TN, we found out the d-spacing, which is seen to be around 3.5% higher than that of the pristine cathode material, which suggests that it would have a better diffusion kinetics of sodium ions. Through the elemental analysis, we observed that even in the primary crystals, the elements are uniformly distributed. We then tested the electrochemistry against a sodium cell and cycled it within a potential window of 2.5 to 4.3 volts. And at a current rate of 0.1 C, both the NMTNO nano and micro gave us a similar voltage profile. However, the capacity obtained from NMTNO nano was much greater, which was around 153 milliamp hour per gram, with a capacity retention of more than 94% after 100 cycles. So we also tested the rate capability test in order to see the reversibility of the sodium ions, as because we have made nano, so it would be giving a shorter diffusion pathway for sodium ions, and it was seen that according to our hypothesis as well as the experiments, this performed very well even when at a higher C rate of 3C. However, in contrast to that, the NMTNO micro suffered 23% loss. And it is to be noted that as the C rate increased, the performance of NMTNO micro degraded further. So which is why we tested it for the long cycle life, and we observed that just after 200 cycles, the NMTNO nano gave us a capacity retention of around 95%. However, that of NMTNO micro reduced to only 72%. This could be attributed to the fact that the NMTNO micro is suffering from diffusion-induced stress, as well as which leads to exfoliation and cracking, and thereby less utilization of the active material. We then saw the morphology by collecting the electrodes after 10 and 100 cycles at 0.1 C, and we saw that just after 10 cycles, the NMTNO micro initiated the cracks and exfoliation, which aggravated further after 100 cycle, and in fact after a higher C rate of 0.5 C, we observed that it broken down into various multiple sheets, which was also evident through the high resolution TM, where we could easily see the distorted lattice fringes. However, in contrast to that, we do not observe exfoliation in the NMTNO nanoparticles even at a higher C rate of 0.5 C and also through the high resolution TM, which suggests that the NMTNO nano was much robust, which retained the structure after prolonged cycling. To quantify this hypothesis, we conducted the fracture mechanics analysis with the help of Mr. Jeet Ghosh, and we considered particles ranging from 25 nanometer to 25,000 nanometer, and we charged it at a C rate of 1 C. And we saw that with increase in dimensionless radius and increase in time, the tangential stress kept on increasing, which suggests that the particle size has a crucial role to play. To understand the effect on the C rate, we considered two extreme particles of 25,000 nanometer and a 500 nanometer. So the 25,000 nanometer particle has been shown here, which shows that with increase in C rate, the flaw size, which is basically the initiation of the exfoliation and cracking, is increasing, and the stress intensity factor is seen to be increasing exponentially. To conclude this analysis, we predicted an electrochemical shock map, which tells us about the critical region of toughness for this kind of layered oxide structures. To further validate the practicality, we fabricated a full cell against the biomass-derived pre-sodiated hard carbon anode, and we cycled it at a current density of 0.14 milliamp per centimeter square, which gives us a first cycle discharge capacity of 1.22 milliamp per centimeter square. However, the Coulombic efficiency was only 90.4%, which further increased to 98% from the second cycle onwards. And the capacity retention delivered was around 85% after 200 cycles. Hence, in this particular chapter, we dealt with the problems of diffusion-induced stress, the exfoliation and cracking, air moisture instability, and poor electrolyte percolation by making nanocrystallites of NMTNO, which in contrast to the bulk size that suffers through stages of microstructural damage, has higher surface area, easier electrolyte percolation, lesser effective current density, and uniform particle geometry, thereby bridging the gap between the microstructure and the electrochemical properties. However, there is still attention needed for the problems such as the irreversible P2O2 phase transition, the partial irreversibility of oxygen redox, the voltage hysteresis, transition metal dissolution, and chemomechanical degradation. Hence, in the next chapter, we actually found out the impact of heteroatom doping in elevating the cycle life. So we have seen that the exfoliation and cracking is a major cause. However, the reason behind this is the irreversible P2O2 phase transition, which we dealt with by doping niobium. So we have chosen niobium because of its robust bond with oxygen that stabilizes the host structure, reduces the electronic band gap that would actually improve the electronic conductivity, and also has a lower diffusion barrier, thereby expediting the sodium, the electron and the sodium ion transfer. So we start by synthesizing the niobium doped NMNO cathode, and the phase confirmation was done through XRD refinement. And when we visualize this XRD refinement through the structure, we observe that indeed doping niobium has actually increased the C-axis parameter, reduced the A-axis parameter, and also increased the sodium-oxygen bond length. So another important factor for the longer cycle life is the sodium-ion diffusion pathway, which we, with the help of Professor Dan Major's group, we found out that we considered two pathways. The first case in which the sodium ions are occupying only the edge shared phases, and the second case, which is a much practical one, where a sodium ion is sitting in the phase shared space in between two edge shared voids. So in this case, we observe that the pathway diffusion period is much lesser in comparison to that of the pristine one. And through the electron localization function, we also identify the nature of the bond, which shows that the niobium oxygen bond is much more ionic in nature, as well as the manganese oxygen. However, the nickel oxygen bond is much more polar covalent in nature. Through the scanning electron microscopy, we observed that we could get a clear hexagonal plate-like morphology with clear facets and uniform geometry. And through the high-resolution TM, we observed that the 002 plane has a D spacing of 0.558. And through the elemental mapping and line scanning, we observed that in the primary crystals, we could successfully dope niobium throughout the crystal, which is very not common, because niobium faces phase segregation and atomic surface rearrangement problem. So this is the first thing we obtained. Then we tested the electrochemical analysis against the sodium metal and cycled it within the potential window of 2.5 to 4.2 volts. And when cycled at a C rate of 0.1 C, we observed that the capacity was more than 149 milliamp hour per gram, with a capacity retention of more than 95% after 100 cycle. And through the DFT analysis, we saw that the niobium doped NMNO is stable over a wider potential window. And also we tested the reversibility through the rate capability test, which shows that even at a higher C rate of 5C, it can retain more than 50% of its capacity. Now, that is the reason why we tested the long cycle life at a higher C rate of 1C, which shows that it gave us a capacity of more than 90% after 2000 cycles. So this suggests that the niobium doped NMNO cathode has been successful in suppressing the phase transition. However, in order to visualize that, we conducted the in situ X-ray diffraction analysis, which showed that during charging, the 002 plane, which is the main responsible plane for the sodium ion diffusion pathway, shifts towards the lower 2 theta. However, it is to be noted that it doesn't go to the O2 phase, but becomes a distorted P2 phase, which returns back to its original position after fully discharged. So in order to have the accuracy, we did the cycling at a very slow rate of C by 15 and utilized the full potential window of 2.5 to 4.3 volts. This was also validated through the energy difference calculation between the P2 phase formation and the O2 phase formation, which shows that the niobium doped NMNO is less susceptible to phase transition in comparison to that of the pristine one. Since in situ X-ray diffraction is also related to the gas evolution in the structure, we conducted a real-time monitoring of the gas emission through the online electrochemical mass spectroscopy at a slower C rate of C by 15 and observed that the CO2 evolution was significantly lesser in comparison to that of the pristine one. However, even the oxygen gas was suppressed. So to theoretically understand as well as to visualize the electrode, we first actually saw the SEM morphology of the cycled electrodes after 100 cycles. We saw that there are cracks as well as exfoliation taking place throughout the pristine cathode material, which was very well evident through the transmission electron microscopy as well, which shows the exfoliation of layers not only in the layers but also in the lattice fringes. The exfoliation was very well visible, which was absent in the case of niobium doped NMNO, even in the lattice fringes, as well as it is to be noted that niobium, even after cycling, was uniformly distributed over the crystal. So the theoretical investigation started by identifying where does niobium get stored, which is at the nickel site. And through the PLOX calculation, we observed that there has been a lowering of the band gap, which suggests that it has a better ionic mobility in comparison to that of the pristine one. Through the COHP calculation, we try to understand the bond strength, and we see that the nickel-oxygen bond strength becomes stronger with dissociation, whereas the other transition metal, which is manganese oxide, remains constant. And also the sodium oxygen, which is the weakest among them, is also constant, but it is important that the niobium oxygen bond strength is the strongest and also doesn't change with dissociation, which suggests why did we obtain a suppression of the oxygen gas loss in the online electrochemical mass spectroscopy. So we integrated a full cell out of it as well, and we considered the pre-sodiated biomass derived hard carbon, and when cycled at a current density of 0.13 milliamp per centimeter square, we saw that it gives us a capacity retention of around 93% after 100 cycles. And when we optimized it in the 0.6 cell, we also fabricated a single layer pouch cell, which also gave us a capacity retention of around 86% after 100 cycles at a current density of 0.109 milliamp per centimeter square. Thus, in this particular chapter, we could successfully suppress the P2O2 phase transition, in fact inhibited the formation of the O2 phase and improved the sodium ion kinetics, thereby improving the cycle life by doping niobium homogeneously across the crystal, making single crystals, and also thereby not inducing any kind of atomic scale surface reorganization and preserving the entire structure through prolonged cycling. Still, there are certain challenges that are yet to be addressed. The first one being the partial irreversibility of anionic redox reaction, the voltage hysteresis, the transition metal dissolution, and chemomechanical degradation. So, in the next working chapter, we try to trigger the mechanism of anionic redox activity. So, we have seen that how gas evolution and during electrochemical cycling is a serious problem in terms of safety. So, this happens when we are charging at a higher voltage. Apart from the phase transition, there is also electron transfer that leads to structural disorderness, this reduction in the oxygen-oxygen bond, and also the formation of transition metal and peroxolite species, leading to consequences such as oxygen gas loss, irreversible capacity loss, voltage hysteresis, and structural degradation, along with poor electrochemical performance. So we adopted the strategy of doping a higher valent cation species, which is ruthenium. So we start by optimizing the amount of ruthenium that would be useful for actually getting the proper anionic redox activity, which would be partially irreversible. So we found out that the 0.16 doped ruthenium is giving the better result in terms of phase purity as well as the electrochemical analysis. And we could see that through the XRD refinement that it belongs to the P63MMC space group, and the nickel, manganese, and ruthenium has a honeycomb ordering structure. And through the SEM as well as the TEM analysis, we observed that the hexagonal plate-like morphology exists with a very clear facets and uniform regular geometry, and the d-spacing for the 002 plate is 0.561. It was important to identify the nature of the bond in order to actually see whether the anionic redox reaction will be possible through ruthenium doping or not, which is why we conducted the electron localization function, and this topological graph shows here. In the first case, we have a pristine cathode material where the sodium ions has been extracted, so it is 0.50. We have the ruthenium doped at the pristine state, which is the 0.67 sodium, and the extracted state at 0.50. In all the three cases, the common thing is that the manganese and nickel oxygen bond is ionic and covalent in nature. However, the ruthenium bond is more covalent in nature, and also as we see with extraction of sodium, it becomes stronger. This is a very important thing in order to stabilize the structure during anionic redox reaction. So we also tested the electrochemistry against sodium metal within the potential window of 2.5 to 4.3 volt. The pristine cathode material shows a capacity of only 100 milliamp hour per gram and also suffers substantial capacity fading. And the ruthenium doped one gives us a capacity of 175 milliamp hour per gram, which is higher than the theoretical capacity, as the theoretical capacity is 161 milliamp per gram. And it also gives us a capacity retention of around 93% after 1000 cycle at a higher C rate of 1C. So further, we also saw the voltage profile, and it was seen that the ruthenium doped one offers a slight higher potential in comparison to the pristine one. However, what is important is the beta charge analysis, which confirms the oxidation of O2P, and also it was seen that the ruthenium oxygen and the ruthenium ions and the oxygen ion activity increases with dissociation. So it tells us that oxygen is actively involved in the redox process. Further, to study the electronic and the bonding properties, we conducted the DFT analysis and saw that ruthenium is doped in the manganese side. And through the beta charge analysis, we observed that the band gap was 0 electron volt after doping ruthenium, which can be attributed to the D states provided by the Ru4 plus ions. And through the COHP calculation, we saw that in this case, the nickel, the manganese, and the ruthenium oxygen bond strength increases with dissociation, and the ruthenium oxygen bond strength is significantly strong. So we further analyze the PDOS calculation of the ruthenium and oxygen because the major criteria for anionic redox reaction is the overlap of the d orbitals of the metal and the sp orbitals of the ligand, which was seen that at the 0.67 state, which is the starting phase, ruthenium 4 plus is successfully through the band diagram we can see that ruthenium 4 plus is successfully overlapping that of O2 minus. And it is to be noted here that it is a myth in anionic redox reaction that it has to be alkali rich in order to conduct anionic redox activity. However, we have seen that in spite of being sodium deficient, which is our starting is any 0.67, we could still achieve anionic redox reaction. And not only that, at 0.33 when the sodium ions are extracted and the initiation of the anionic redox reaction take place, we see that we get bonded O2 minus, which in comparison to that of the alkali rich are underbonded, which leads to loss of oxygen from the lattice, which is a disadvantage in that case, which we have improved. And we further verified that through the Fickey functions. So using the Fickey functions, we actually tried to figure out the chemical reactivity of ruthenium when an electron is removed and when an electron is added. So we observed that ruthenium still stabilizes the entire structure when the electron is added or removed. We also studied the redox mechanism through the Zane's analysis and observed that the nickel is the electrochemically active element, and it was seen to go from the 2 plus to the 4 plus state, and the increased intensity of the pre-peak also tells us about the environment of the local coordination environment of the nickel. Through the XPS analysis, we found out that indeed peroxolite species has formed when the material has been charged and the XPS has been taken at the charged state. And this was further validated through the redox population calculation theoretically as well, which shows that nickel is active as well as the oxygen. So through the in situ analysis of the X-ray diffraction analysis at a slow rate of C by 50, we observed that during charging, the 004 plane, which is attributed to the changes in the MO6 octahedra, was seen to shift towards the lower 2 theta, which suggests that during this point there has been reduction in the ruthenium-ruthenium bond and also the ruthenium-oxygen bond, which leads to the shrinkage of this MO6 octahedra, giving these variation during charging, which returns back to its original position after one full cycle. So we also verified it through the lattice parameter changes and observed that the change in A and the change in C parameter was much lesser in comparison to that of the pristine cathode material, which suggests again that the ruthenium is able to stabilize the entire structure. Since we are seeing here about the oxygen loss, we conducted the online electrochemical mass spectroscopy at a slower rate of C by 15, and we observed that the CO2 gas has actually suppressed and the oxygen gas evolution has significantly suppressed, which suggests that definitely ruthenium is able to stabilize the structure with the help of the ligand to metal charge transfer mechanism. That is why entire ruthenium is holding the structure. So the morphological evolution tells us that the pristine particle, when charged at a higher C rate at till 4.3 volt, gives us cracks exfoliation, which is also visible through the high angle annular dark field imaging, which was absent in case of the ruthenium doped cathode material. So in this particular chapter, we dealt with the partial irreversibility of oxygen redox, voltage hysteresis, as well as gas evolution by doping ruthenium and activating the ligand to metal charge transfer mechanism in order to make it partially reversible. So there are certain challenges that are yet to be addressed, which is the transition metal dissolution and chemomechanical degradation. So as of now, we have seen that we were discharging the cathode material till 2.5 volt. So we had seen through the DFT analysis that the niobium doped NMNO was much more stable over a wider potential window, as we had already seen in the previous slides. So that is why we chose that particular cathode material and discharged it till 1.5 volt in order to get the advantages of increased overall capacity, the incorporating the manganese redox activity, and also get higher energy density out of it, and finally utilize the full electrochemical potential window. However, there were certain consequences that we felt, which were the structural degradation, the manganese dissolution, increased SEI, and capacity fading, voltage hysteresis, and shorter cycle life. In order to deal with this, we adopted the strategy of surface coating through an unconventional atomic surface reduction technique, where we choose an organometallic compound, which is trimethyl aluminum, as a precursor, and then pass it through the vacuum reactor at a low temperature of 200 degrees Celsius, which marks its advantages over the ALD technique, atomic layer deposition technique. This vacuum reactor consists of the cathode material, and then once it has been pulsed, we see that we get an aluminum treated cathode material which gets attached to the plate. So we start by choosing the trimethyl aluminum precursor because of its high reactivity, the ability to decompose at a relatively low temperature, also because it easily gets attached to the functional groups and thereby enhances the conductivity. So we do the comparison between the XRD of the untreated as well as the treated material, and we observe that there's hardly any change in the bulk structure, except for the fact that the FWHM of the treated was narrower in comparison to that of the untreated one. And through the DFT analysis, we observe that the trimethyl aluminum gets attached at the 104 plane. Through the FEPTEM analysis, we observed that we were successful in obtaining a uniform coating, and through the high resolution TM, we observed that there hasn't been any change in the bulk because the D-spacing remains of the 002 plane remains same as of the pristine cathode material. Through the SEM analysis of EDS analysis of the secondary particle, we observed that aluminium is only on the surface, whereas sodium, nickel, manganese, and niobium are homogeneously distributed throughout the crystal. So we interfacial characterization using the TOF-SIMS analysis, and we observed that when we probe the surface and the bulk using the TOF-SIMS analysis, we see that aluminium through the 3D rendering map is only there on the surface. In fact, through the depth profile analysis, we observed that the aluminium can be seen only till 40 nanometer, and the untreated one do not show any peaks of the aluminium. And the claim that the niobium has been uniformly distributed into the bulk, we were seen through the TOF-SIM analysis as well, which shows the presence of niobium throughout the crystal, ranging from, it starts from around 5 nanometer, which shows that niobium is not undergoing any kind of atomic scale surface reorganization. Through the XPS analysis, we observed that the aluminium peak can be attributed to the oxidized state, and the nickel and manganese in the pristine state is at 2+ and 4+ state. We tested the electrochemical analysis against sodium metal and observed that the voltage that the capacity that we obtained is around 155.6 milliamp per gram in comparison to that of the untreated. And as we cycle it till 1.5 volt, we observed that manganese has been activated. The reversibility was tested through the rate capability test. And through the diffusion coefficient analysis using the scanning of the cathode material at different scan rates, we observed that yes, manganese is active, and also the diffusion coefficient is around 10 to the minus 7 centimeters square per second, which is lesser in comparison to that of the untreated one. So we cycled it at 400 cycles at 20 degrees Celsius and observed that the treated one gives us a capacity retention of around 87% after 100 cycles. However, it is to be noted that the acid corrosion and the manganese dissolution gets elevated at a higher temperature, which is why we conducted the cycling even at 60 degrees Celsius, which shows that the treated one performs much better in comparison to that of the untreated one. And finally, to see the manganese content, whether there is manganese dissolution taking place, we conducted the ICP analysis of the separator and observed that the manganese content in the separator after cycling in the untreated sample is much more in comparison to that of the treated one. So we then found out that the CO2 evolution after coating has actually become minimized when we monitored it through the online electrochemical mass spectroscopy, and it is almost zero. So this tells us that indeed the coating has been advantageous for the problem of manganese dissolution, and thereby understanding the problem that has been done. So we further to see how the chemomechanical degradation is happening, we did the SEM as well as some FIP-SEM analysis and high annular dark field imaging, which easily shows the cracks, the complete cleavage, corrosion, exfoliation, pit formation, and the corroded edges is also very well visible in the primary crystals. We then analyzed the charge compensation mechanism using the XPS, and we saw that at charge state, the nickel as well as the manganese both are active, and also through the Zanes analysis, we observed the activity of nickel as well as manganese. Thus, in this particular chapter, we dealt with the challenge of transition metal dissolution, the HF corrosion attack, the chemomechanical degradation, CO2 gas evolution, and thermal degradation by adopting the strategy of coating the cathode material with the trimethyl aluminium as a precursor. In order to have a comparative study in the conclusion chapter, we considered all the three cathode materials, the titanium, the niobium, as well as the ruthenium doped. And we observed that although in terms of cost, the titanium is cost effective, however, in terms of performance and considering all the other stability as well as the raw material analysis, the niobium doped NMNO would be economical, as well as because we could easily suppress the P2O2 phase transition. So some of the future scope work that we can have out of this work are scale up and manufacturing considerations, the advanced characterization technique to investigate the anionic redox activity in details, and then electrolyte modification by in situ cathode electrolyte coating, and then exploration of high entropy P2 type cathode materials, the multifunctional study through co-doping strategy, adopting the strategy of high sodium content, and definitely we can have an all solid state battery. So these are the outcomes of my working chapters and some of the other contributions. These are the patents that we have filed and they are under examination, and the book chapters that we published. And I was fortunate enough to attend some of the conferences. So I would like to, actually PhD is never a one-man job. It is always a group of people who have always been there. So first and foremost, I would like to start by showing my deepest gratitude to Professor Sagar Mitra, my supervisor. He has actually not only trained me for this particular work or this dissertation, but he has trained me for the ultimate goal of mine, which I think thanking him would be too less of this. So I don't think it is enough to thank him. No words can thank him for whatever he has done, and it is because of him that we are seeing this day. I would also like to thank him for the opportunities that he has given us and also the facilities that he has provided. And I would like to thank my funding agencies, the MNRE and the SCRB for funding the work. I would also like to extend my thanks to my RTC members, Professor Amatya Mukhopadhyay and Professor Dayadev Mondar. And I would like to thank them for their insightful guidance as well as the comments during all the annual progress seminars, which has definitely helped in my research. I would also like to thank my collaborators, Professor Tanmay Bhandakar from Mechanical Engineering Department, for helping us understand the fracture mechanics analysis, Professor Malaki Lokit, who had actually hosted me in Barilan University in order to conduct the in situ experiments and the atomic surface reduction technique, and also Professor Dan Major for helping us with the DFT analysis. So I would like to thank my chairperson, Professor Singh, for taking out his time and coming here and chairing the session. Professor Barpanda for coming all the way along from Bangalore for the defense and also reviewing my thesis very critically, which has definitely enhanced the work. And also Professor Dhaka for giving his time and the insightful comments he has provided. So all the past members of the ECL lab mates as well as the present lab mates, I think they are the family we have here, and they've been always very supportive for anything. And I think there are certain people who are there beyond lab. I think the support is very important. And I would firstly like to thank Mrs. Mitra. Ma'am has been like an elder sister to me. She, like, I could go to her for anything, like anything, and she has been a true source of inspiration for me. And also, I had a few very good friends and very limited friends. So, Dr. Nupur Goswami and Miss Shemunti and Miss Rajeshi. Rajeshi is here to support me today as well. So, thank you so much for their enormous support. And last but not the least, my family. And I think it is because of them that I'm here today. Whatever I am, it's only because of them. They've been the backbone and the full support that they have provided. And thanks to each and everyone for being here today and supporting me for the defense. Thank you so much.
Wonderful work. I learned a lot. So now over to the external examination.
Congratulations. Good quantum of work. So I want to ask some clarification questions followed by some general questions.
Right.
So first thing is, you go to slide number 8. So in general, I mean, we are taking some